In this video, we're going to do section 3.6, asymptote. So let's get started with our first definition here, infinite limit. So an infinite limit is the type of limit in which f of x, so that's some function that we're looking at, approaches infinity or negative infinity. Alright, so that is why it is called an infinite limit, as x approaches c, so some number c that's in the domain of f of x, from the left or from the right is an infinite limit. So the type of limit in which f of x approaches infinity or negative infinity is x approaches c from the left or from the right. Alright, so we'll go into more detail in a second, but let's define vertical asymptote first. So for a vertical asymptote, if f of x approaches infinity or, again, negative infinity, and I might just start using the infinity symbol instead of writing that out, as x approaches c from the right or from the left, then the line x equals c is a vertical asymptote of the graph of f. Alright, so these definitions are sort of similar in the sense that they have a lot of the same words, but they're not, they're definitely not going to be the same. So we'll go into that a little bit more in which cases you would care about which types of limits in a little while. So let's first go ahead and define the limit at infinity. So where did that definition go? Well, if I can find it here. Alright, so limit at infinity. Alright, so limit at infinity says that if, and I really don't like that color. I know I'm colorblind, but I don't like that color. If, well, here it is again. If f, that is very strange. Alright, is a function and L1 and L2 are real numbers, the statements of the limit as x approaches infinity of f of x equals L1 and the limit as x approaches negative infinity of f of x equals L2 denote the limits at infinity. And finally, horizontal asymptotes the lines of y equals L1 and y equals L2 are, well, horizontal asymptotes. So horizontal asymptotes, I think, oh, I missed a T, there we go. Asymptotes of the graph of f. Alright, so let's get started now that I have laid the terms and concepts down for you. So here we go. Let's do an example. Vertical asymptotes and infinite limits. I realize why now you saw a different color there. So hopefully this will show up the color it was originally. One of the most common instances of a vertical asymptote is the graph of a rational function. So that is a function of the form f of x equals p of x over q of x. So that is just our typical rational function where the denominator cannot equal 0. So p of x and q of x are polynomials. And if c is a real number such that q of c is equal to 0 and p of c is not equal to 0, actually that one should be p of c. Alright, there we go. P of c not equal to 0, then the graph has a vertical asymptote at x equals c. So if the denominator is equal to 0, because remember q of c was the denominator, and the numerator is not equal to 0, then the graph has a vertical asymptote. Now if they're both equal to 0, like 0 over 0, then we have a different problem that we're not going to address at the moment, at least. Alright, so let's do example 1 then. So consider the function 1 over x. So hopefully you would agree that this is definitely a rational function because it has a numerator that's a polynomial, 1, which is a constant polynomial, and the denominator x, which is a polynomial because it's a linear function, y equals x. So this is a rational function. So if we want the limit as x approaches 0 from the left, so this little minus sign means limit as x approaches 0 from, and that little minus sign will mean from the left. Alright, so here is 0 right here, and this side is to the left of 0, and this side is to the right of 0. So if I look to the left of 0 and I look at what this graph is doing, this graph is going on and on and on downward. That means this limit ends up being negative infinity. And if I look at what this is doing, this little plus sign here, this little superscript here means the limit as x approaches 0 from the right. So if I look to the right of 0, here's 0, and here's to the right of 0, and I look at what the graph is doing, it's going up and up and up forever. Which means this limit is infinity. Alright, so hopefully that all made sense by just looking at the graph, because now we're going to try doing this using a different method, so a numerical method. So example 2, find the limit as x approaches 2, and remember this little plus sign right here is going to mean from the right, and the limit as x approaches 2 from the left, so from the left of x squared plus 3 using numerical methods. So numerical methods just mean generally we're going to use a table of some sort. So here is our table x, and then the function was x squared plus 3. And then numbers to the right of 2, that just means greater than 2. And from the left of 2 means really just, it's just going to mean less than 2. So I want to substitute some numbers in that are really, really close to 2, but still less than 2 or still greater than 2. So 2.1 might be good, or 2.01, or 2.001. So I want to get as close to 2 as I can, but still be greater than 2, or to the right of 2. And then some numbers that are less than 2, but still really close to 2. So like 1.9, 1.99, and 1.999. These are all to the left of 2, or numbers that are less than 2. And if I substitute these in, 2.1 squared plus 3. Now, if you don't want me to spoil it for you, you can pause the video for a second, but this will be 7.41, 7.0401, 7.004001. This will be 6.61, 6.9601, and 6.9960001. And I see that the closer I get to 2 without actually substituting 2 in, that the value I'm getting is getting really close to 7. So both of these limits end up being 7. Alright, so that's all I mean by numerical methods. Now, I think what you need to be careful of is remember that the limits from the right and from the left aren't always going to be the same. Like in example 1, we saw one of them was negative infinity and the other one infinity. So you might think, oh, I could have found this limit easily, but I do want you to realize that not all of them from the left and the right are always going to be the same. Alright, so now it is time for example 3. So let me move this down so that we can do example 3. So find each of the following limits if it exists. So there are, again, multiple ways to do this, but I'm going to try to stick to the numerical method for us. So this is the limit as x approaches 1, and remember that little negative sign there means from the left. So that means that I'm going to substitute numbers in that are less than 1, but really close to 1. So x in negative 1 over x minus 1 squared. So numbers that are less than 1 but close to 1, 0.99, 0.9, and 0.999. If I substitute in these, I get negative 100, negative 10,000, and negative 1 million. Now, if you do one more of these, which I don't know if I want to set a limit on how many that you should do. I just want you to make sure that you are going to be comfortable with your answer at the end. So 0.9999 should be negative 100 million. So these numbers are getting astronomically small very, very quickly. That means that this limit ends up being negative infinity because these numbers are going to negative infinity. All right, so the limit is negative infinity. All right, so let's look at example B now. So let's go to example 3b. So this is limit as x approaches 1, and this will be from the right. So from the right means that we're going to put in numbers that are greater than the 1 that's right there. So x 2 plus x over 1 minus x. So 1.1, 1.01, 1.001. And if I substitute in these numbers, I get negative 31, negative 301, and negative 3001. And one more, just for the sake of it, it looks like you can get the pattern here, but 30,001. So these numbers are also getting very small very quickly. So these are going to negative infinity, and that is what this limit is. All right. Hopefully this is all making sense, but I'll do another example here for you. So 3c, this one is the limit from the right again. So this is the limit from the right, and that means that I want numbers that are going to be greater than the 2. So x and 2 minus x over x squared minus 4. So here are some numbers that are greater than 2 but close to 2. 2.1, 2.01, 2.001. So if I plug in these, I get 0.2439, negative 2494, negative 2499. And I I really want you to think about how this is different than maybe the ones that we just did in the previous example, because these numbers are not getting to be very, very small necessarily. So if I substitute in 2.000001, I get negative 0.24999999375. I think that these are all fairly close together, and they're about negative 0.25, and that's actually what this limit ends up being. Alright, so that's how this one is a little bit different, and why you do have to really pay attention to these and make sure that you're substituting the numbers in correctly. Alright, last one on this page here. So I'll go to letter D for you. So same thing, we have limit as x approaches 10, and that will be from the right because of that little plus sign there. And so that means we're going to substitute numbers that are greater then 10n for x, so x in those bars are absolute values, so please try not to forget that. Some numbers could be 10.1, 10.01, and 10.001, and these all end up being 1. So these are all exactly the same, so this limit ends up being 1 here. And I think that you may have figured that out from the absolute value, maybe not, but if the limit was from the left, the answer may have been different, but you should definitely try that out for yourself. All right, let's go to example 4 then. So find the vertical asymptote of the graph of f of x equals x minus 5 over 2x minus 1. So to find the vertical asymptote, remember that the vertical asymptote from our definition at the beginning occurs when the denominator equals 0. So 2x minus 1 equals 0, add the 1 to get 2x equals 1, and then divide by 2 to get x equals half. So then we need to verify that x equals a half is a vertical asymptote, and we do that by showing that the limit as x approaches a half from the left of f of x, or the limit as x approaches a half from the right of f of x equals plus or minus infinity. It doesn't matter which of the limits you show, and it doesn't matter whether it equals infinity or negative infinity, just that one of them equals this. Alright, so here we go. Let's just show this one right here. So I'm going to show the limit as x approaches a half from the left of f of x, which was x minus 5 over 2x minus 1. So if I substitute in some numbers that are to the left of a half, but really close to a half, I might pick numbers like, I don't know, 0.49, 0.499, and 0.4999. So this gives me 222 or 225.5, 2,250.5, and 22,500.5. And I see these are getting really large, so this limit is infinity. Therefore, since we showed it was either infinity or a negative infinity, x equals a half is a vertical asymptote. Alright, but that's what we set up here, but we just verified that. I know how some of you in the class really like verifying things. Alright, so hopefully that example made some sense, but we'll do another example of that here right now. So find the vertical asymptotes of the graph of f of x equals x squared minus 1 over x. So I know that if this has a vertical asymptote, it's going to end up being at x equals 0. So that's where this denominator would be undefined. And if you really, I think, want to make it a little bit easier for yourself, maybe then you could find the common denominator, which would be x. So that would be multiplied by x over x. And then Oh, there it went back to that other color again. Alright. Minus 1 over x, so that's x to the third minus 1 over x. So still, we know that the vertical asymptote, and I'm going to abbreviate it VA from now on, occurs when x is equal to 0. So now we're going to verify that x equals 0 is a vertical asymptote. And we're going to do that again by finding the limit as x approaches 0 from the left, or the limit as x approaches 0 from the right. It doesn't matter which one, so I'm going to choose this one. The limit as x approaches 0 from the left of x to the third minus 1 over x. So if I make a little table here, then some numbers to the left of 0 but close to 0 might be negative 0.01, negative 0.001, and negative 0.0001. If I substitute these in to f of x, I get 100.00001, 1,000.00001, and well, 10,000. So these are getting astronomically large, so it is infinity or negative infinity. It didn't matter which one, as long as we got infinity or negative infinity. So therefore, again, that's my symbol for therefore, x equals 0 is a vertical asymptote of f of x equals x to the third minus 1 over x. Alright, so very good. That is the end of this page here. So let's go to the next page. So we'll talk about, instead of vertical asymptotes, now horizontal asymptotes. So a limit at infinity specifies, where's my pen? So let me bring this pen back up here. Nope, I don't like that color. A finite value approached by a function as x increases or decreases without bound. So note that it is possible for a graph of a function to cross its horizontal asymptote. So the reason why this is important is because, in contrast, a graph will never cross its vertical asymptote. Alright, so please try to keep that in mind, that a graph can cross its horizontal asymptote, but not its vertical asymptote. Now, just to clarify the difference between what we were talking about in the last part, but not in this part on horizontal asymptotes. In the last section on vertical asymptotes, we were finding infinite limits, so I don't know why I drew extra either. So, and back to that other color again. Infinite limits. So infinite limits were these types of limits. Limit as x approaches a half from the left of f of x, and then we got infinity. And now we're going to be talking about limits at infinity. And this is the limit as x approaches infinity of f of x, and then this will be a number like a half. So the difference is that for infinite limits, the answer is infinity. For limits at infinity, the number that x is approaching is infinity or negative infinity. Alright, so please try to remember that. Like even for this first example here, find each limit at infinity, we see that infinity is the number that x is approaching. So let's do an example here. Find each limit at infinity. And actually this first one should be an x right here and not an n anyway. So the limit is x approaches infinity of 2 plus 3 over x squared. Alright, so here we go. Now remember this infinity is right down here now. So what I'm going to show you in these next few sections here, the next few examples here, you can only use if x is approaching infinity or negative infinity. So I'm going to break this up into the limit as x approaches infinity of 2 plus the limit as x approaches infinity of 3 over x squared. Now hopefully you remember this limit is 2, but what you may or may not have remembered is the limit as x approaches infinity of c over x to some power, or a number over x to some power, is always equal to 0. So this limit right here, based on this rule that I need you to really remember, is going to be 0. So 2 plus 0 is 2. Alright, so that is an example of this. So let's try another example. So let me move to part B. The limit is x approaches negative infinity. So please remember what I was just talking about. If this is negative infinity or infinity right here, then we're going to use a different technique. So again, here is going to be the technique, since this one is a little bit harder than the first one. We're going to look for the highest power of x in the denominator, which is x to the second. And then we're going to divide every term by the highest power of x in the denominator. The key word is in the denominator. So this will be the limit as x approaches negative infinity of x over x squared minus 1 over x squared all over x squared over x squared plus 1 over x squared. So everything gets divided by the highest power of x in the denominator, which is x squared in this case. Then I'm going to simplify limit as x approaches negative infinity of 1 over x minus 1 over x squared over 1 plus 1 over x squared. And then anything that has the x still in the denominator is going to have a limit of 0. So 0 minus 0. Alright, so this goes to 0, that goes to 0, and this will go to 0. Over 1 plus 0 will end up being 0. Alright, let's try again. So, the highest power of x in the denominator is the x. And then we see that we want the limit as x approaches infinity. So if this were anything here except for infinity or negative infinity, we cannot use this technique. So the limit as x approaches infinity of x cubed over x over x minus 2 over x. Then I simplify. Limit as x approaches infinity of x squared over 1 minus 2 over x. So now anything that has an x in the denominator goes to 0 now. So this will just be, well, if I substitute in, well, here, let's do that limit. So 1 minus 0 is 1. So its the limit is x goes to infinity of just x squared over 1. And so that's just x squared, and that ends up being infinity, because infinity squared is just, well, even a bigger infinity. Alright, so hopefully that technique made some sense, because now we're going to do one more. So let me move to part D here. Limit is x goes to infinity. Now, we're going to make sure this is infinity again, or negative infinity, and look for the highest power of x in the denominator. So that's x squared. Limit is x goes to infinity of 3x squared over x squared over x squared over x squared plus 2 over x squared, which is the limit as x goes to infinity. Let's simplify that now. So 3 over 1 plus 2 over x squared. And anything with the x in the denominator now goes to 0, since 3 over 1 plus 0, or just 3. Alright, so this could get a little bit harder, but not really. Alright, now let's go on to the specifics of horizontal asymptotes of rational functions. So let f of x equal p of x over q of x be a rational function. If the degree of the numerator is less than the degree of the denominator, then y equals 0 is a horizontal asymptote. And if the degree of the numerator is equal to the degree of the denominator, then y equals a over b is a horizontal asymptote. And if the degree of the numerator is greater than the degree of the denominator, then the graph of f has no horizontal asymptote. So there's 3 cases here, so make sure that you're clear on them. Less than the degree of the denominator, then y equals 0. Equal to the degree of the denominator, then y equals a over b. And then greater than the degree of the denominator, then no horizontal asymptote. Alright, so let's look at these examples here. Find the horizontal asymptotes of the graph of each function. So f of x is equal to 3 plus 2 over x. So this is not a rational function yet, but I can write it as 1. So that 3 over 1 plus 2 over x, and I multiply by x over x to get a common denominator. So 3x plus 2 over x. And then I look for the degree, and each of these highest powers terms have the same degree, so the degree of the numerator is the same as the denominator. So the degree of the numerator is 1 because of 3x to the first power. The degree of the denominator is 1. So that means that because the degrees are equal, the horizontal asymptote is going to be y is equal to the ratio of those two terms, 3x over x, or just 3. Alright, so hopefully that all makes sense of how I found that horizontal asymptote. Let's try another one. Maybe this one will make a little bit more sense if that first one did not. So this one we did not have to find a common denominator because it just f of x is 3x minus 1 over 4x plus 5. So the degree of this numerator is going to be 1, and the degree of the denominator is also 1, so they are equal. That means your horizontal asymptote is y is equal to 3x over 4x, or 3 over 4. Y is equal to 3 over 4. Alright, let's try again. This next one will be a little bit trickier. If you thought that you had it, hopefully you still do. So, the degree of the numerator is going to be 1. Now, the degree of the denominator is also 1 because that x squared is in the square root, and the square root of x squared is just, well, x. Alright, so these are actually equal. So the horizontal asymptote is y is equal to 2x over x, which means that this is going to be 2. Now, here's the other comment, that the square root of x squared is actually plus or minus x, so if you didn't also find 2x over negative x and get negative 2 as a horizontal asymptote, the struggle would have been real for you. Alright, so y equals 2 and y equals negative 2 are both horizontal asymptotes in this case. Alright, so let's try example D. So the degree of the numerator here is going to be 2. And the degree of the denominator is going to be 1. So what I really don't like that color. So I know if the degree of the numerator is greater than the degree of the denominator, then that means that f of x has no horizontal asymptote. So please try to remember that for the rest of your life. Alright, the next 2 pages are just pages that are here to give you some other examples of things that you might see on your journey through calculus and some additional examples. I'm not going to go ahead and find the slant asymptotes, but because I just want to focus on the horizontal and the vertical ones, and I'm not going to go into some special cases because although these are really nice looking graphs, they still reiterate the same point that a graph can cross its horizontal asymptote but not its vertical asymptote. Now for everyone's favorite part, the application of asymptotes. So the cost C in dollars for a company to recycle X tons of material is C is equal to 1.25x plus 10,500. Find the average cost C bar. So C bar is going to be C over X. So the cost divided by the number of units will give you the average cost per unit. So it's 1.25x plus 10,500 over X. And then we want C bar when X is equal to 100 and when X is equal to 1,000. So X and C bar is 1.25X plus 10,500 over X. So if I substitute in 100, I get 106.25. I'll let you try that on your own. I know how excited all of you are. And if X is 1,000, I get 11.75. Alright, now, that was the easy part, hopefully. You just need to remember to find the average cost. You're going to divide by the number of units x. So then part C, determine the limit of the average cost function as x approaches infinity, and then interpret the limit in the context of this problem. So that would be the limit as x approaches infinity, so as x approaches infinity, of the average cost, which is the limit as x approaches infinity of 1.25x plus 10,500 over x. So if you recall how I did this, I divided every term by the highest power of x in the denominator, and then any term that still had an x in the denominator after I simplified would go to 0, so 1.25 plus 10,500 over x over 1. So this will go to 0 because it still had an x in the denominator, so it's 1.25 plus 0 over 1, or 1.25. So in the context of this problem, it says that as the number of units x goes to infinity, meaning increases indefinitely, the average cost will level out at 125, meaning that you can't ever get cheaper than 125 to recycle a ton of material. But the more tons of material you recycle, the less the average cost will be per ton, but you cannot get cheaper than $1.25 per ton. I mean, who really likes to recycle anyway? That's my real question. I see all of you out there who like to recycle. Example 9. I mean, maybe the next time you're just thinking about this, you could think to yourself, well, is that really a garbage truck going down the road in Clinton Township, or is it a recycling truck? Example 9. The cost C in dollars of removing P% of the air pollutants in the stack emission of a utility company that burns coal is modeled by, you can see it here, C is equal to 85,000 P over 100 minus P, where P has to be between 0 and 100 including 0, meaning that the cost could be based on removing 0%, but you can never actually remove 100% of the air pollutants. So find the cost removing 15%, 50%, and 90%. So P, and then 85,000 P over 100 minus P. So 15%, 50, and 90. I'll let you check these numbers on your own, but I'm getting 15,000, 85,000, and 765,000. And then I want to do part B here. I think part A is easy, just substituting in the numbers. But if I want to find the limit as P approaches 100, and this will be from, remember that this is from the left, meaning that the numbers are less than 100, then interpret the limit in the context of this problem. So we want the limit as P approaches 100 from the left of 85,000 P over 100 minus P, and some numbers that are to the left of P but less than, well, 100. So the left of P equals 100 but less than 100 could actually be 99.9, 99.99, and 99.999. And so that will give me 8491500 and 849915000 and 8499150. Oh, I'm missing a 9. Oh, I'm missing a 9. 000. So you can see that these are getting astronomically large, so this will be infinity, meaning that therefore it is not possible for all of the... Oh no, what did I do here? I somehow made it larger and I didn't even realize it. The air pollutants to be removed. Alright, so what a time to be alive. We just finished this section 3.6. What a time to be alive.